Hello everyone. Okay, this is our first course about finite elements. So we will make a very short introduction about computers and how we use it in engineering, specifically in mechanical engineering. Okay, we design tools for daily life for people, and we want to predict their behavior in general. So this is then we can design some better tools. Of course, the main thing that we are interested in mechanical engineering is the response of the structure when a force acts on it, or response of the object when there is temperature variation, or if there is a flow around or inside it, for example in case of a pump or a pipeline. So this is what we want to do, and we want to design better products for people. And of course it's very difficult to do it with theoretical tools which we have seen in strength of materials or in machine elements. So now the computers give us better capability of designing better tools and we can use them. Certainly when we use computers we deal with the numbers, because the computers can only understand numbers. Okay, so this is the thing. Perhaps you remember the truss systems. What we do is we write the force equilibrium for each junction. Then we have a set of linear equations, and we solve that set of linear equations in order to find the forces acting on each truss element. There are several different types of numerical methods. Finite difference is one of those which you have seen in numerical methods course. There exists finite volume, which is commonly used in fluid mechanics, and of course finite element is another method, another approach which we use. You can use finite element for fluid flow analysis, for stress analysis, or for heat transfer problems. Now within this course we are going to see how the basis of the finite element method and how it works. So simply just think that you have a simple plate with a hole inside it. Okay, so and just think that there is a force acting on it from in one direction, for example, regardless of the material. So it can be steel, plastic, PMMA, aluminum, or whatever it is, whatever the material is, you will see a stress distribution. Now it's very difficult to find the stress distribution, and because you need to find the maximum stresses, right, in order to be sure that this design is safe. So okay, it is very difficult to do it with one-dimensional theories that we have used in strength, but perhaps there are analytical methods which we use in elasticity, but it may not be probable for complicated geometries. It may not be probable to find an analytical solution for complicated geometries. For example, you may have a bracket, or you may have some other tools. So here is a stepper motor. Okay, as you see, it has a flange, it has a shaft. So certainly motor rotates this shaft and the force and torque is transmitted to somewhere, and of course there is a stress distribution, and it is completely three-dimensional, and finding the stress distribution in order to design a better step motor for three-dimensional problems is almost impossible. So what we do is we use computers and we make an approximation. Okay, so we use numerical methods. We have seen how we use the numerical methods for solving some mathematical problems. Now the point is, what we do is in finite elements, first thing is we divide the domain of interest into subdomains. This is the first step. You may divide one edge into 10 and or maybe to 40, 50. So it depends. Certainly at each node, we are going to see it in detail, at each node we have some unknowns and we generate a set of linear equations at the end, and then we solve these set of linear equations. And within this course we are going to see how we do it. So we need computers because even if you have 10, each of these subdomains are called elements. So even if you have 10 elements along one edge, which basically means that you have approximately 100 elements in total and more or less 100 nodes. So nodes are the points at the edge. We will see. You have 100 equations to solve, or you may have 2000 equations. You may have millions of equations. So what we do when we have such a large problem, we use computers, luckily. Okay, so let's look at the computers. I mean, the development of the computers. Now, of course, the first computer was considered to be ENIAC, which was developed in 1950s. So at that time the CPU times are very low, and as the time passes we have better computers. Then we have IBM, CDC, Cray, and so on. We have parallel computers. Now today we are using computers with thousands of processors. And look, this is the PC that we are using at the moment, the speed of the PC that we are using at the moment, and look at the computers in which were manufactured in 1970s, 1990s. So even the PCs that we have at home are much more faster today. Okay, how about the price? Now, of course, in the old days of engineering, what you do is you make a first order approximation, as we did in simple approximation, as we did in strength of materials, and you design a tool. Then you make experiment. Now luckily, of course, experimentation is quite expensive because you hire a person, you pay for the salary, you need to manufacture the prototype, and then you test it, and you need a testing facility to do it. All these are costs. But if you have a computer and the software to make this analysis, it's better, it's cheap. So let's look at the prices. In 1968, a computer with a 1 million floating point operations costs about $8 million. Okay. Now, at that time there was no personal computer. Engineering salary in United States per year was $9,000 at that time, and the professor at the time was earning $11,000. Okay, a tuition of a university is $2,000 approximately, and it goes like this. So a car costs about $3,000, a Mercedes costs about $7,000, and so on. Okay, when we come to the 2005, a 1 teraflop computer costs about $500,000. So approximately 16 times cheaper, and the speed is 1 million times much. Oh, not yeah, 1 million times. So 10 to the power 6 times faster. Look, now we have at homes 2 million 2 million floating point operations computers, 200 millions, and the cost is from $500 to $3,000. Look at the first computer and look at the price that we have at homes now for the computers. Okay, the engineering salary increases approximately 5 to 6 times, but the computer price decreases more than 1,000 times, and so on. Okay, so basically the cost of computations significantly decreases within time. So computation and computers are cheap now compared to the experimentation and testing. What we can do with the finite element analysis, we can do several things. Now, people are using robotic surgery, and we want to predict the force acting on the tissue in order to design a better surgical robots. And you want to make the analysis. It's highly complicated because your hand is a viscoelastic material. Okay, so it behaves like both like a fluid and both like a solid at the same time. So you can use computers to make such kind of an analysis when the material behavior is very complicated, or you want to design an heart valve for somebody because he may have some heart disease. Of course, the geometry is highly irregular, and as a result, you can use computers in order to analyze such kind of a structure. You want to predict, you want to design a car and you want to predict its response. You want to design the suspension system, you want to design the exhaust system, or you want to predict the drag and lift forces around an aircraft. Again, highly complicated geometries. But the good thing is you can do it in computers because you divide all the domains, all the volumes or areas into sub areas which are almost regular. Or there may be a problem of pollution, or you want to predict the weather tomorrow, and you just measure the weather conditions at the moment, because what you do is you have sensors, you have pressure sensors or anemometers. You measure the wind speed, and then you measure the pressure, you measure the humidity, and you put it into the code, and you make a simulation and you predict the weather for tomorrow. Or if there is a pollution, you want to see how it will be spreaded by the weather conditions or environmental conditions. So this is what you do. Even now we are using such kind of analysis tools in order to predict, for example, how the COVID disease spreads. Okay, so this is what we do. Of course, we need some tools in order to make it understandable for the computer, and the first tool that we use is mathematics. So again, we return back to the mathematics because mathematics is the language of engineering. Just imagine that you have a concrete column. What we do is we just take a very small tiny piece from it, okay, and you know that it is microstructure. The inner structure is highly irregular and it is very difficult to model it, even if you look at the problem from different scales. So even if you get into the structure, you get in more deeper into the structure. So what we do is, okay, we use mathematics and we basically assume that the properties are homogeneous by using the mathematics, and we solve such a problem. We use material models, right? For example, if the material is elastic, we use the theory developed for the linear elasticity. If we are even want to predict the behavior of the composite material, then we use anisotropic stiffness tensor and we homogenize the model, let's say. So we have an homogeneous model, and then we give it to the computer. So mathematics tells the computer that it's unhomogeneous, but the computer doesn't know it. So it solves just what we give it, what we give to the computer. Okay, for example, here we have a porous structure. You see it is highly complicated. We have very short ligaments, and of course you can predict the stress distribution inside such kind of a structure by using computer models, by modeling it. You may have again highly irregular structure which is made from beams, for example. So remember how we solve the truss systems. Just imagine that each beam here is acts like a truss. Then if you have 1 million truss elements, how you can solve such kind of a problem? You want to predict the forces at the junctions and you want to know whether it will fail or not. Again, we use computer simulations. Of course, you can predict the stress distribution in such kind of a complicated structure very easily. It is just at a cost of some software and computer. Okay, this is a short introduction about the course and what we are going to see within this course.